Well, this is the graph of f of x equals square root of x on the interval from 0 to 1. Let's look at it. There it is. Aren't you glad you looked at that? We're going to find the average rate of change on this interval. We know how to find an average rate of change. That's essentially a slope. So let's do that very quickly. And we're going to represent it by what we see on the graph as well. So we're going to do f of 1 minus f of 0 over 1 minus 0, y2 minus y1 over x2 minus x1. We're basically finding the slope between, let's make it green, that rhymed, between here, and we could connect those if we wanted to and find the slope that way, but we're going to do it this way first, and then you'll get a visual for it. So let's see, plug in a 1, get a 1, plug in a 0, get a 0, 1 minus 0 over 1 is going to give me 1. So if I drew this line in green, because I feel like it, I drew this line right here from here to here, the slope would be 1, which I think is fairly obvious. Okay, now the next part is a little wordy, but that is basically the mean value theorem. Now, I'm not saying the mean value theorem is wordy, but you'll see questions that are worded this way. Find the x value on which the derivative, okay, pause. Answer is going to be an x value. We're going to need a derivative, and that derivative is equal to the average rate of change. So let's find the derivative of the square root of x, which I think we know already. So f prime of x equals 1 over 2 square root of x. There we go. You can do it all kinds of ways. X is x to the 1/2, and then you take the derivative, but there you go. There's that. And we are going to set this equal to the average rate of change, which is 1. And we're going to solve this. So we'll cross multiply in a sense. So 2 square root of x times 1 equals 1 times 1, so 1. And then the square root of x equals 1/2. So we'll square both sides, and we have 1/4. Okay, what does that tell me? Now, let's not read the next part yet. You can if you want to, but I'm not going to yet. Let me explain what just happened, and that is essentially the mean value theorem. So mean meaning average. We found the average rate of change on the interval from 0 to 1, and then we found the x-coordinate, and sometimes there's more than one, but in this case there's one. We found the x-coordinate, which is at 0.25, it's 1/4, it's right here, where the slope is equal to the average rate of change. And so here's what that really means graphically. If we drew the line tangent to this curve, which we'll get to in a second, and we drew it just perfectly, it would be parallel to that, meaning this. Here we go. There is at least one point on this curve, in this case exactly 1, where the slope is equal to the average rate of change on the interval. There's an exception. We'll get to that when we fill in some stuff here. But in the meantime, we have that slope, which equals that average rate of change. It's kind of cool stuff. Okay, find the equation of the line tangent to f of x at the point where the derivative is equal to the average rate of change, and then we'll draw it too, which we've already done. So y minus y1 equals m x minus x1, just a little bit of practice with tangent lines. So y minus y1, which would be 1, equals m, the slope at that point, which would be 1/4, and then x minus x1, and so y equals 1/4 x, and then we will add 1. Something feels very wrong about that. I'm wrong, I've done that wrong, and I'm not starting this video over. I apologize deeply for what just took place. Wow. So sorry. Okay, wow. I just said that m was 1/4, x is 1/4. Oh dear. Okay, lesson learned. Let's read the problem very carefully. Man, that's terrible. Here goes. Y minus the y value at the point where the derivative is equal to the average rate of change. I was using this point. No, that's not a point. That's an interval. I have to be careful. Even math teachers make mistakes, and I don't want to edit it out. I'm going to go with it, okay? Be careful. But sometimes you get to the end and you realize it doesn't make sense. And let me tell you what went through my head. I think it's a good lesson to learn here. The slope is 1. We found it. And here I said the slope was 1/4, and I got down here and my y-intercept was off. My y-intercept was 1 and my slope was 1/4. Like, no, that's not that line. That's not it at all. Okay, so y minus what? Well, I don't know yet, but what I do need to find out, and I'll find it out over here, is f of 1/4. because this is the x value, I need the y value that goes along with that. That would be the square root of 1/4, which of course is 1/2. So y minus 1/2 equals the slope, which is 1, and then x minus 1/4. That's the x value. This should work out better. 1x minus 1/4, we add 1/2 to negative 1/4, and we would get positive 1/4, and that's much better. Slope is 1, y-intercept is 1/4. Okay, let's talk about the mean value theorem and what it means. You have to meet some conditions. This is an existence theorem, like the intermediate value theorem was an existence theorem. We're basically saying there is something that exists, and these are the conditions you have to meet. So if f is continuous on a closed interval, and differentiable on the open interval, let's just stop right there. We have to meet a couple conditions, and here's condition number 1. F is continuous on the closed interval from A to B, and differentiable on the open interval. And we can get all uptight about what's open and what's closed in terms of this, but what we really look for is, and this is most of the time is what we look for differentiability. Now, we have to meet all these conditions like to a T, but if we have differentiability, we have continuity. And now it depends on if the interval is open or not, but there we go. Okay, let me clarify that a little bit. Let me finish and then we'll clarify that. Then there exists a number C, some x value. I think that's worth writing. So we're going to say that C is an x value, at least one number C, in AB, open interval, such that what? Such that what? Well, I'm glad you asked. Let me write it down for you. We'll write it in blue. No, green. Got your hopes up on blue. That the slope at C is equal to the average rate of change on the interval. Okay? So here's where we're going with this. We are going to do a series of problems where we will find the average rate of change, find the derivative, and set them equal. If we have met some conditions, condition number 1, continuity on a closed interval. Okay, continuity on a closed interval like this. Check this out. You don't have to draw it. You can just kind of watch. We're going to go from A to B, and we're going to have a function that is continuous on a closed interval from A to B, and it's going to be like something like that, which is sort of what we had here, okay? And it has to be differentiable on the open interval, and here's what that means. I don't care about the slope at A or the slope at B, because that goes, if I wanted the slope at a point at the end point of an interval, then, well, that doesn't quite work because I'd have to go beyond the interval, okay? And if that didn't make sense, don't panic. I need continuity, and I need differentiability in between A and B. And as long as I have differentiability, then there is at least one C value. Let's get a ruler here. You'll see where this is going. You'll see where this is going. Then there's going to be at least one C value where the tangent line has the same slope. Here, we could just kind of bring it out like that, and there it is. Boom. That's it. This dot right here, that is a valid C value according to the mean value theorem. Okay, let me talk about what would happen if we did not have differentiability. So, different example right here. We're going to go from A to B. And we'll go, let's see, we'll have continuity on the closed interval, but we won't have differentiability. We got this really weird, almost absolute value-ish looking thing, but it's a piecewise function. So I can find the slope between those 2 points. And that's fantastic. But nowhere is that same slope represented because the function is not differentiable. Okay? So it's not fair to draw a tangent line here. The tangent line here wouldn't exist. The slope doesn't exist at that point because the derivative doesn't exist at that point. Same thing though. All right, A to B. Let's do one more. Let's suppose we have a function that's not even continuous. Let's get some sort of crazy asymptotic thing going on. So we have some, vertical asymptote. Function's not even continuous. Now, if you want to find the slope between these 2 points, you go for it. You have fun. It's great. But it really doesn't mean anything because we can't find a point between here and here that has the same slope. And even if we could, it may not be valid because we we basically violated the mean value theorem. We don't have continuity, so we can't guarantee that that happens. Okay, there's the mean value theorem. In the next few videos, we're going to apply it.